Welcome to 5.4. I want to start this section by making a comparison between area and volume with you. So if you go back to your single variable calculus days, if you wanted to compute the area of this region here as a single integral, you would integrate from 0 to 2, and then you'd integrate the top curve minus the bottom. So 6 minus x minus 2x dx, top minus bottom. And I went from 0 to 2 because those are the values on the x-axis for which I have my region. Okay, to do that as a double integral, we would integrate the function 1, and I'll do it as a dy dx. And our y limits, y starts at the curve 2x, and it ends at 6 minus x. And again, x goes from 0 to 2. Now, if you were to evaluate the first integral in this double integral, you would be right back here. Now let's do volume. Let's set up the volume of this region here as a double integral. So we're going to integrate top minus bottom. Again, the top surface now is 8 minus x minus y, and the bottom surface is 1, and we'll go dy dx again. And to get my xy limits, I think it would be helpful to take this picture here and put it into the xy plane so I can see it better. So this is y equal 1, and this is y equal x. So there's our region right there. So if we do our y limits next, y would go from x to 1, and x would go 0 to 1. Now what's new is we can do this volume as a triple integral. So if we just compare with what we did above in analogy, we would now integrate the function 1 dz dy dx, and our z limits would be the lower surface down here, 1, and then the upper surface, 8 minus x minus y, there. And then the y and x limits stay the same. And again, if you were to do the first integral on that guy, you would end up back over here again. Now, to evaluate a triple integral, it's no more difficult than evaluating a double integral. And so I'm going to set this problem up with you, but I went ahead and did the 3 integrations for you right here, and you can read that on your own. So we want to integrate 2z dv over the region S, and S is given by this set of inequalities. So we don't even have to graph anything here because the inequalities are given right to us. Z goes from 0 to xy, y goes from 0 to 2x, and x goes from 0 to 1. And the function is 2z, and the order that we did that in was dz, dy, dx. All right, but the fun part is the setup. And so let's do some setup problems. Finding limits of integration. We want to set up a triple integral for the volume of the solid pictured here in 2 different ways. So first I want to go dz dy dx. So if I'm doing z first, I want to imagine vertical lines going through the solid. Those vertical lines enter on this plane here. That's the plane z equals 0. And they leave on this plane here, which is z equal 1 minus y. So our z limits are 0 to 1 minus y. Now for the xy limits or yx limits, I'm going to draw another picture, and I'm going to project that region down onto the xy plane. And if I do that, this is x and this is y. This would be 1 right here, and this is 2 right here. So it's just a rectangle. And so now I can do the limits on the other 2 integrals at one time. So we've got a triple integral. We're doing volume, so we're going to integrate 1, and we're going dz dy dx. Z we know goes from 0 to 1 minus y. Y goes in my picture over here from 0 to 1, and x goes from 0 to 2. Now let's do the setup again, but we're going to do x first. So if x is coming first, then I want to imagine lines that are parallel to the x-axis going through the solid. So I've got a picture over here of a line going through the solid. It's entering on this plane here. That's the plane x equals 0. And it's leaving over here on this plane. That's the plane x equal 2. So the x limits are 0 to 2. And then I'm going to do my yz limits together by projecting against the yz wall. And so I'm going to draw a yz picture. This is y. And this is z, and you can see that you're going to get a triangle, and this is the line, y plus z equal 1, so that's z equals 1 minus y, and if I'm going to do z next, I want to think of vertical lines, so my triple integral I can set up, we're going to go 1 dx dz dy, x goes from 0 to 2. Z goes, from my picture over here, from 0 to 1 minus y. And y goes from 0 to 1, because this is 1 right here. All right, let's do another setup. Again, two integrals, but this time z is going to come first for both of them. So I only need one picture. Since z is going first, I want to imagine vertical lines going through the shape. They enter on the plane z equals 0, and they leave on this plane right here, which is y minus x. Now for the xy limits, I want to project that region onto the xy plane. And when I do that, I'm going to get a triangle. Down here, this is the line y equal 1. So that's this line. And then this line is y equals x, because in this equation, if I set z equals 0, I get y equals x. So this is y equal x, and there's my region. So I'm going to get two integrals for that, and I've got a blank space down here. Unfortunately, it's on the second page. So I'm integrating the function 1, and I can put the z limits in on both of these because they're the same. Again, we're integrating the function 1. You don't need the 1 there. Now, if I go y next, I want to think vertical lines. Y goes from x to 1, and x goes from 0 to 1. If I want to go x after z, then I want to think horizontal lines. X is going from 0 to y, and y goes from 0 to 1. And I'm going to end with an application of average value using this formula right here. F average is 1 over the volume times the triple integral of the function you're averaging over the solid you're averaging. So in this case, we've got a tetrahedron right here, and we want to find the average value of this function here, temperature, over that region. So the first thing we have to do is find the volume of the region. So that's step 1. So in this tetrahedron right here, this plane that you're looking at is z equal 1 minus x minus y. So we can see that our z limits are 0 to 1 minus x minus y. For the xy limits, we project that tetrahedron onto the xy plane. This is the line y equal 1 minus x. This would be 1. So if I set this up as a triple integral in the order dz dy dx, then the z limits are 0 to 1 minus x minus y. The y limits in this two-dimensional picture right here, they start at 0 and they go to 1 minus x, and then the x limits are 0 to 1. So this is just for the volume of the tetrahedron. We haven't worried about the temperature yet. So integral 1, 0 to 1 minus x minus y dz. So I'm integrating the function 1. That would be z between 0 and 1 minus x minus y, which is 1 minus x minus y. So integral 2, we'll put the limits for the y variable, 0 to 1 minus x, and we'll integrate the answer from integral 1, which is 1 minus x minus y, and this is a dy. So we're doing the middle integral. Okay, so I want to think of this as 1 minus x minus y. Remember, x is a constant when you're integrating with respect to y, and so is 1. So this is simply 1 minus x, that constant, times y, minus 1/2 y squared between 0 and 1 minus x. I'm trying to work smart, not hard. I'm seeing a 1 minus x in a bunch of places. I want to keep it together. So if I replace y with 1 minus x in this term, I get 1 minus x squared. And then for the second term, I'm going to get minus 1/2 1 minus x squared. And then when I put in y equals 0, I just get 0. So this is the result of my second integral. And I'm going to combine like terms. If I take 1 minus x squared and I subtract half of that, I'm left with 1/2 times 1 minus x quantity squared. Make sure you can follow that. Okay, so integral 3 is the integral from 0 to 1 of 1/2 1 minus x quantity squared dx. Now, there's several ways you could do this. You could multiply it out. You could do it in your head. I'll just do a quick u sub. U is 1 minus x. Du is negative dx. So negative du is dx. So this is going to be negative 1/2. I'll pull the 1/2 out. Integral of u squared du. And we have to change our limits. When x is 0, u is 1. And when x is 1, u is 0. I'm just going to leave it in this order. This is negative 1/6 u cubed between 1 and 0, which is 0 minus negative 1/6, which is 1/6. So that's the volume of the tetrahedron that will go right here in this formula in the denominator. The next step is to do this part, triple integral over the region. So the limits will be the same on the next integral, but the function will be the temperature function. So I've set that up right here. Notice the limits are the same as our last integral. I put in the temperature function, and my order is dz dy dx. Now, this is going to be a very ugly integral, although nothing's too difficult. I strongly suggest you use Symbolab. That's what I did. It will do triple integrals. Here's an image right here. And it gave me a fraction and a decimal. And so then to do the final step, which is F average, I take 1 over the volume. 1 over 1/6 is 6. And then I take the answer from my triple integral and put it here, and I multiply, and bam, there's my answer. Okay, and that is the end of this section.